Hi there, and thank you for your interest in µD3TN. This video is the second part of our µD3TN trilogy. If you haven't seen the first part yet, we recommend watching it first. There we introduced challenge networks, explained the basics of the delay and disruption-tolerant networking architecture, and provided a high-level overview of µD3TN. This video, however, is intended to give a short demonstration of how to use µD3TN. You will learn how to download and compile the application, how to start it, configure the necessary contacts between two instances of µD3TN, and eventually how to send bundles between them. First of all, it is assumed that all following commands are launched on a POSIX or Linux system. A virtual machine or Docker container will work for this purpose too. Before we download µD3TN, we have to make sure that we have installed all the necessary dependencies. If you have a Debian or Ubuntu-based system, you can install them using the shown commands. On other distributions, you might need to adapt the package names. We need GNU make, Benutus, and GCC. Moreover, we also need Python 3 distutils and curl for setting up the Python environment, Python 3 for using the µD3TN Python tools, and Git for working with the code repository. In case you need help, feel free to contact us. We will gladly assist you. There are two possible options to get the source code of µD3TN. The first one is to use Git to clone the repository from GitLab by using the shown commands here. If you click this link below, you will get to a page where all the different µD3TN versions that have been released so far are listed. From there, you can choose a version you would like to use. In the short demonstration that I'm giving you now, I'm going with version 0.11.0. The other option is to go to the page that I've mentioned before, select source code including dependencies to download the zip file and eventually unpack it somewhere. Now that we have gotten the source code, the next step is to build µD3TN via the command make POSIX and to run it via make run POSIX. This will launch a new instance of µD3TN with the default parameters. When everything is set up, the daemon will continue running and can be terminated as usual via sigint or sigterm. Let's start with our small scenario where we will perform simple disruption-tolerant data forwarding. Basically, we have two µD3TN instances representing two nodes, a source node and a destination node. You can call them whatever you want. I'll go with instance A and instance B. They are connected via the minimal TCP convergence layer adapter, or MTCP-CLA for short. Our goal is to send a bundle protocol version 7 bundle from the sending application connected to the first instance to the receiving application connected to the second instance. Those two applications are both written in Python. The following procedure can be divided into 5 steps. First of all, we will launch instance A where, among other things, the TCP ports that shall be used will be defined. Then we will repeat the same process with instance B. After that, we have to configure a contact between those two instances. We will define how long the contact lasts and when it starts. Then a receiving application will be attached to B. That way, B will be able to receive bundles from A. And finally, we will attach a sending application to instance A, which will enable A to send bundles to B. We will begin by launching the two instances. To launch instance A, we will enter the following command. This will tell µD3TN the node ID, the bundle protocol version that we are using, the TCP port that is used for the application agent protocol, and the port the MTCP is listening on. The MTCP serves as the only convergence layer adapter in our scenario. The asterisk sign tells µD3TN that MTCP should listen on all interfaces. For this step, you can continue to use the shell that you have been using for the previous commands, or you can also open another shell. The only thing that is important is that you have to be in the µD3TN base directory. You can switch there via cd UD3TN. For launching instance B, we will open another shell and enter the following code. You see that we've just increased the port numbers by 1 to avoid a collision. Please note that we will have to run all terminals in parallel, so do not close the previous shell. I will use another text color in order to make it more apparent to you which terminal I am currently using. Now both µD3TN instances are up and running, and we can continue with configuring a contact from A to B. µD3TN needs to be configured in order to know which DTN nodes are reachable during which time intervals and with which data rates. This configuration occurs at runtime and is not permanent. Therefore, you have to reconfigure µD3TN after each start. To simplify the configuration process, we provide a Python tool for that purpose. However, in order to use it, we have to make sure that the Python dependencies are installed. The easiest way to do so is using the development setup. By running make virtualenv in our µD3TN directory, we create a Python virtual environment in .venv and install all necessary dependencies. That step you will only have to execute when using the Python virtual environment for the first time. We can activate the virtual environment via the shown command. I will demonstrate this procedure to you later when we configure the contact. As we need the Python dependencies every time we run a Python command, we will have to repeat this step multiple times. If you want a more detailed explanation of that, you can check out this link below, or in case you want to get a better understanding of virtual environments in Python in general, feel free to read the article accessible via the following link. Now that we have the Python dependencies installed, we can finally enter the command below to configure a contact from A to B. This specifies that aap-config.py shall connect to localhost on TCP port 4242 via AAP and issue a configuration command to the µD3TN daemon. The contact is defined by the schedule argument. It starts 1 second from now, runs for 3600 seconds, and has an expected transmission rate of 100,000 bytes per second. Of course, you can change these values as you wish. For example, you can also configure a contact at a later point in time. Until then, µD3TN will queue all bundles received for a given node. The last two arguments specify with which DTN node ID the contact is expected and via which convergence layer address the node is reachable. You will see that instance A will attempt to connect to instance B 1 second after this command has been issued, given that you have entered the number 1 for the first parameter. If nothing went wrong, instance B will accept the connection. Please note that instance B will not be able to send bundles to instance A, as MTCP is a unidirectional CLA. For sending bundles the other way, you need to configure another contact from instance B to A. Before we continue, first let me demonstrate the previous steps to you. We will start by activating the virtual environment in a new shell. The .venv at the beginning of the next line indicates that it is activated. After that, we will be able to use the given Python tool for configuring a contact from instance A to B. Only 2 more steps to go. You remember the scenario setup that I have shown you? We have now managed to launch instance A as well as instance B and to configure a contact between those two. The only things that are left to do are attaching a receiver to instance B and finally sending a bundle from A to B. In order to attach a receiving application, please open a new terminal and enter the command below. This requests µD3TN instance B on TCP port 4243 to register a new application with the agent ID bundlesync. Now the full endpoint identifier will be the following. As you can see, we are using another Python tool for this, so don't forget to activate the Python virtual environment in the new terminal. If nothing goes wrong, aap-receive.py will wait for incoming bundles on that socket connection and print their payload to the console. Now we are finally ready to send bundles via the established contact. Please open another terminal and enter the given command. This will ask µD3TN instance A on TCP port 4242 to create and send a new bundle to the given EID with any payload data you would like to transmit. Let me quickly demonstrate this step to you. In our example, I'm going with the message, "Hello µD3TN users." After this, you should be able to see the receive bundle appear in the output of AAP-receive.py. Although the setup may seem complex at first, you will actually find it quite straightforward to interact with µD3TN instances as soon as you have managed to play through the whole scenario once. For a deeper understanding, you can take a look at the code of the provided Python tools and libraries that you will find in our GitLab repository. This may help you to develop your own integration someday. There's also a written documentation of the scenario that I've just shown you, in case you want to quickly look something up without rewatching the video. If you have any questions or want to contribute something, do not hesitate to contact us. Of course, we will also be more than happy to help you integrate µD3TN into your own networking project. As I have mentioned before, we strongly recommend you watch the first video of our µD3TN series in order to thoroughly understand the technical aspects. There will also be a third video where we show you how we use µD3TN in our RedMars project that has been made possible with funds from the Federal Ministry of Education and Research in Germany. Thank you for watching the video and see you next time.